For Lab 5, I decided to explore the energy principle using a system with translational and rotational kinetic energy. I found online a video of people rolling in a tire down a hill, two individuals, something I've always thought was fun but never did, and I computed the gravitational potential energy of the tire at the top of its incline, and then through Tracker analyzed its motion and found its kinetic translational energy. And with that, I attempted to find the rotational kinetic energy based on the energy principle, assuming that this was a closed system with only gravity acting on it. Here's the video in Tracker. I did my best to keep the center where I was tracking. I used the calibration as the individual on the left's leg, and I made several other assumptions in this experiment, such as the mass of the tire. I just used the average weight of two adult humans who were the people in the tire, plus the mass of the tire would be that for a standard big rig tire, which was roughly 90 kilograms. For the calibration, like I said, I did 0.7 meters for the individual's leg, which is just a rough approximation. Net force, I said, was only gravity. The height was also approximated, and the tire wasn't perfectly at rest nor stopped during the duration of the video clip, but it was the closest I could get throughout the Python code I created for this lab was very similar to Lab 4, since they both dealt with energy. VPython cannot find or cannot model rotational motion in the same way it does translational or spring. So that in itself motivated me to kind of find that value in a different way, because I would have to do more assumptions also, such as finding the moment of inertia and also create another while loop to try and calculate that. So here's my code. As you can see, looks very much like Lab 4, like I said. And unfortunately, I can't get VPython for some reason to show the graph every time I press run. It just shows a blank white screen. However, I did get it to print the values I needed. So my concluding results were, to summarize again, the rotational energy was determined to be 8,027 joules. Hinges on the previous assumptions that I stated. Several sources for error I identified could be camera angle was definitely not perfect. My assumptions were not perfect. Other forces or friction could leak unaccounted energy into the system, which would also affect the values and make it not a perfect example of conservation of energy. However, this basic principle should still apply, and the value I obtained seems reasonable within the constraints that I applied to this system. So essentially, this is the only energy that could be in the system, being its potential when it was on the hill. The individual on the left, who I calibrated it with, did give the tire a small push, which was unaccounted for in my model. However, it was mainly gravity which was pulling the tire down the hill, so I believe this value is fairly a good jumping off point. And that concludes my presentation.